At this point, we know enough calculus to graph a function. Graphing combines everything we know about functions, from intercepts and asymptotes to intervals of increase, decrease, and concavity. Let's graph the rational function f of x equals x squared divided by 16 minus x squared by finding its intercepts, asymptotes, the intervals of increase and decrease and any relative extreme values, and the intervals of concavity and any inflection points. The x-intercept is found by setting y equal to 0. Then 0 equals x squared, which means 0 equals x. So the x-intercept occurs at the origin, 0, 0. The y-intercept is found by setting x equal to 0. We get y equals 0, which gives again the origin. To find the vertical asymptote, we set the denominator equal to 0 and solve for x. This gives x equals positive negative 4. To find a horizontal asymptote, we look at the limit of the function as x goes to positive infinity and negative infinity. In both cases, we get negative 1, and so y equals negative 1 is the equation of the horizontal asymptote. This tells us the end behavior of the function. To determine the intervals of increase and decrease, we need the first derivative. Using the quotient rule, we get the following. Then we set this equal to 0 and solve for x. Then x equals 0. This is the critical point. Now we build a sign chart around this critical point and around the vertical asymptotes. Using test values from each interval, we determine that the sign of f prime of x is negative, negative, positive, and positive, which means the function is decreasing, decreasing, then increasing again, respectively. Between the second and third intervals, the graph goes from decreasing to increasing at x equals 0. This means that x equals 0 is a relative minimum. Finally, let's look at the intervals of concavity and determine if there are any inflection points. For this, we need the second derivative. Setting this equal to 0 and solving for x gives no solution. So the second derivative does not have any critical points. This means that there will be no inflection points in the graph. So when we make our sign chart, we will just make it around the vertical asymptote values. Then using test values to plug into the second derivative, we get the sign of f double prime of x to be negative, positive, and then negative, which means the graph of the function is concave down on the first interval, concave up on the second, and concave down on the last. Again, there is a change in concavity between each interval, but because x equals negative 4 and x equals 4 are not in the domain, they cannot be inflection points. Then the graph is as follows. Notice from negative infinity to negative 4, the graph is decreasing and concave down. From negative 4 to 0, the graph is decreasing. Then from 0 to 4, the graph is increasing. Between negative 4 and 4, the graph is concave up, and it attains its minimum value at the origin. Then from 4 to infinity, the graph is increasing and concave down.